SSH was invented in 1995 by Tatu Jolonen after he discovered a password sniffer running on his university network in Finland and realized, holy crap, we need encryption for remote connections. Before SSH, everyone was using Telnet and our login, which sent everything in plain text, including passwords, which is insane when you think about it. Today, we're breaking down exactly how SSH actually works at the packet level, the encryption negotiation process, and the advanced features that make SSH way more powerful than just a secure terminal. Back in the 70s, when Telnet was invented, sending unencrypted packets wasn't a huge concern because the internet barely existed. If you connected to a remote machine, it was probably in the same building on the same campus network. But as the internet grew and connections started crossing public networks, anyone sitting in the middle could intercept credentials in plain text. That's exactly what happened at Jolenen's university. Someone was running a packet sniffer, capturing usernames and passwords as they flew across the network. SSH fixed this by encrypting everything, so even if someone captures your packets, all they see is encrypted gibberish. They can still see that you're making an SSH connection, and they can analyze packet frequency and size, but they can't read the actual data. It's like your neighbors seeing packages delivered to your house. They know you ordered something, but they can't see inside the boxes. Let's get technical about what an SSH packet actually looks like. At the very beginning, you have a 4-byte packet length field that tells the recipient how big this packet is. Then you have 1 byte for padding length, which specifies how much random padding is in this packet. Next is the payload, which is your actual data, the stuff you care about. After that comes the actual padding, which is random bytes added to make traffic analysis harder. Finally, you have the message authentication code, or MAC, which is basically a cryptographic signature proving the packet hasn't been tampered with in transit. Here's why the padding matters. Even with encryption, an attacker analyzing your traffic can make inferences based on packet sizes and timing. If every keystroke you type sends a 64-byte packet, an attacker might figure out you're typing a password based on the pattern. When the packet gets encrypted, everything except the packet length and MAC gets scrambled. An eavesdropper can only see those two fields. Everything else is encrypted. The encryption algorithm used gets negotiated between client and server during the initial handshake. Both sides can configure which algorithms they accept, and modern best practice is disabling older, weaker algorithms like 3DES or older versions of SSH itself. The payload often gets compressed before encryption, so you're sending more data with less bandwidth, which matters when bandwidth is your bottleneck. Here's where SSH gets really powerful. SSH supports multiplexing, which means you can have multiple logical connections over a single TCP connection. Each logical connection is called a channel. This lets you have multiple terminal tabs all SSH'd into the same server using one underlying connection. You could have one channel uploading files, another downloading data, a third running a text editor, and a fourth acting as an SSH tunnel, all simultaneously over one TCP connection. This is way more efficient than opening separate TCP connections for each task, and it's one reason SSH is so versatile for remote work. SSH can forward X11, which is the windowing system used by most Linux distributions. This means you can run graphical applications on a remote server and have the GUI display on your local machine, all encrypted over SSH. You're basically running Chrome or whatever on a remote server, but seeing the window on your laptop. SSH tunneling is another killer feature. You can tunnel any protocol through SSH to encrypt it or to bypass firewalls. For example, if you need to access a database that only accepts connections from localhost, you can SSH into that server and tunnel the database port back to your machine. Now you're connecting to localhost on your end, but it's actually hitting the remote database through the encrypted SSH tunnel. This works for any TCP service, and it's how a lot of developers access internal services securely. SSH uses public key cryptography for both encryption and authentication. During the initial connection, the server sends its public host key, and your client verifies this matches what it expects. This prevents man-in-the-middle attacks, or someone intercepts your connection and pretends to be the server. For user authentication, you can use passwords, but the better approach is SSH keys. You generate a key pair, your private key stays on your machine, and you copy your public key to the server. When you connect, the server challenges you to prove you have the private key without you actually sending it. This is way more secure than passwords because even if someone intercepts the authentication process, they can't replay it to gain access. Understanding SSH at this level matters because it's the foundation of secure remote access in every environment.